Okay, on to our last page of practice problems. So the first one here, translate the following assembly subroutine to a C function. And so this one is called little endian to big endian, and it's a procedure. It does a rev instruction on R0, R0, and then it BXLRs, so it returns, and then it ends the procedure. So it's pretty short. We're going to want to return a value from this probably, given that we've got something in R0 when it returns. So let's assume that that is an unsigned int, maybe. And we're going to name our function the same thing as it was uh, in the assembly code. So little endian to big endian. And then we're going to take an int value. Or sorry, this should be, pretend that's an unsigned int. That's why you don't do work in pen, especially coding problems. So we're going to have a function here. So that's the same as our procedure, right? That's our sort of equivalent in C, is we're going to have a function where we had a procedure in assembly. And then what this does is it does a rev of the value coming in. So we're going to rev R0, R0, and then BXLR. So there are a few ways you could solve this. I think since we're saying translate to a C function, doing inline assembly to do the rev instruction is not going to be correct. In this case, though, that would be a reasonable way to accomplish this if you were asked to do this, in your job. It would be pretty reasonable to just say, okay, yes, I'm going to apply inline assembly to do this sort of specialized function. But what the question is kind of asking you to do is to, solve this with C code instead. So we have to think about what that rev instruction does, and it takes those 4 bytes of an instruction, and it, flops the endianness of it. So it's going to take that bit and go there. This bit goes here. That set of bytes goes here. That set goes here, and that set goes here. And so that's the operation we're trying to implement, is kind of swapping the individual pieces of this register into another place. And so effectively what we're going to want to do is sort of go through 8 bits at a time and kind of move around these values into the correct place in the new value. So let's go ahead and sort of make unsigned int x equals 0. And let's go ahead and put the pieces of that value where they should be. So we'll just start with, we want to get the rightmost 8 bits, and we want to put them over here. So what we're going to do is we're going to sort of highlight that part of the number, which means that I want to do x is going to be equal to something where we do value ANDed with OXFF. Right? And so the idea here is I'm basically restricting it to just that part of the number, and that gets me the 8 bits that are at the rightmost part. Now I want those 8 bits to end up at the leftmost bits, which if we think it's 0 to 8 or 0 to 7, 8 to 15, 16 to 23, 24 to 31. So I want to take those bits and I want to shift them to the left by 24. And that's going to give me my first value here. And I can set x equal to that because I don't have anything in x yet. Now I'm going to do another operation, and I'm just going to do the next set of bits. So I'm going to do value ANDed with OXFF00. So I'm just now getting those bits here, right? And then I want those to move from here over to here. So I'm going to shift them left by 8 bits. Do the same thing for the next set. So value ANDed with OXFF0000. So we're still moving over another set of bits here. And now I want to go from here to here, so I'm going to right shift by another 8 bits. And then finally, I'm going to OR equals, and I want to get these bits, and I want to move them over here. And actually, in this case, I can be a little, you can do this a little easier, because if we right shift an unsigned value, it's going to do an LSR, right, a logical shift right, which means that it's going to fill with zeros. And so if we just right shift to the correct position, value shifted by 24, that's going to be a little bit cleaner than doing this big AND over there. And in fact, we probably could have done the same thing here, as just, shifted this over and then done the bit mask, and that would have been a little nicer, but that's okay. And then finally, we're going to return x. We do want to keep in mind that, for procedures, if we see R0 and we haven't assigned a value to R0, that's because R0 is the first parameter to a function, so that's the int value that we have here is coming in R0. And then if we assign something into R0 and then BXLR, that's the return value that we're trying to send out of this function. And so that's what we're doing in our C code for the equivalent. So that's it for number 7. Let's move on to number 8. Number 8 is clearly described in the following lines of code do. Answers such as bit x of register y is set to z will not suffice. So we're trying to ask here for a little bit more of a nuanced description of what's happening here. So the first thing you should think is, I need to look at the manual to figure out what's going on with this code. So let's go ahead and pull up the manual. Hopefully by now you recognize that, 4000 is a GPIO-A address or some sort of GPIO address. And let's go ahead and just pull up, to get started, the system memory map. So we could, explicitly search for this address and figure out what's going on here. So let's look through the addresses here around GPIO. We can see that 48000400, that's going to be GPIO-B that's being affected by this. So some port on GPIO-B is being affected. Let's go ahead to the register map and let's see what is at offset C. So if we look at offset C, that's PUPDR, right, or pull up, pull down registers. So this is PUPDR. We need to look at that and see what's being affected and what values are changing. So let's go ahead and find PUPDR in the manual. Here it is. We can confirm offset OXC here. And let's see what bits are being changed. So it's doing an OR of 1 shifted by 22. So in bits 22, we're setting a 1. And then we're doing an AND with a NOT of 1 shifted by 23. So we're doing, in bit 23, we're forcing a 0 by doing a bit clear. So we're looking at 0, 1, which if we look in the manual here says that is a pull-up register. So it's setting a pull-up register, and it's setting that on bits 22 and 23, which are for GPIO 11. So this is pull-up register, or pull-up, sorry, resistor on PB 11. So that would be a good answer for that one. That's what that piece of code is doing. We're just analyzing the same sort of stuff that we've been looking at before, where we've got these places in memory. We are then explicitly setting some values, and we're doing that with the same methods that we've been doing before, which is to do an OR to set a bit, do a bit clear to clear a bit, and clearing a bit makes it a 0, setting a bit makes it a 1. So that's really all we're doing there. How do we enable interrupt for the DAC in the NVIC processor side? So this is actually not in this manual. For this one, we'd have to pull up the syllabus and make sure we can find this if we need it quickly. The place that we have the NVIC table is in the interrupt notes, because that one was not found in the regular manual. So we want to look for the DAC and the ICER 0 and ICER 1 tables. And I don't have this shared, but you can work along with me at home. And what we should see is that we've got TIM6 DAC, and that's probably what we're looking for here. We're really just trying to do name matching on the interrupts to find something that has DAC in it, and that's probably going to be what we're looking for. So yeah, in this particular case, TIM6 DAC is bit 22 of ICER 1. So set bit 22 of ICER 1. So that's really just looking at the manual, understanding that the NVIC is related to ICER 0 and ICER 1 here. What is the address of the GPIO FBRR register? So this is going back to the same table we were just at. We go to page 80 to get started. We'd find, or sorry, 78 to get started. We'd find GPIO F's base address. So that GPIO F base address is OX 4800. 1000. And now we're looking for BRR. In that, we can just use the big register map here if we want to, and we can find that BRR has the same offset as everything else. So our final answer would be 4800, 10, and BR's offset is 28. So that would be it. We're just, really just finding that in the manual, understanding what those names are. And then finally, part D, compare two methods of responding to external events, polling versus interrupts. And so here we want to know what these two things mean. So polling is, that sort of constant waiting in a loop for something to happen. That's what we did in lab 4 when we were, doing loops. We're checking to see, is the button pressed, is the button pressed, is the button pressed, and then if it is, we do something. And so what that gives us generally is a faster response time, because we're constantly waiting for it on the CPU. We're not offloading this to an interrupt that the CPU is handling for us, but interrupts have some cost to them because we have the problem of having to handle the caller saved registers, pushing a bunch of stuff to the stack, redirecting through the NVIC. It's going to take a little bit more time to handle an interrupt. So there's faster response time if you're polling. May be relevant to projects. But uses the CPU constantly. So it's great if we're polling for user input, but if we are trying to do something else, like let's say we're trying to draw graphics on the screen at the same time as we're waiting for a user to give an input. If we're constantly drawing graphics, then it's going to take until we're done drawing graphics to get an input from the user, right? So we can only poll as fast as we can based on what else we're doing on the CPU, what else we're using the processor for. So in some cases it may be better to offload to an interrupt, which is it does not use the CPU. It just kind of offloads, and then we wait for an electrical event to happen or some conversion to finish or a timer to trigger, whatever type of interrupt it is. We're just waiting for something to happen in the background while we can be doing something in the foreground, like waiting for user input or drawing things or doing some other useful task. But there's a slower response time because we have to handle slower response because caller saved registers and NVIC indirection. So we have to do a lot more work whenever we do call an interrupt. That is it. I hope this helps. Sorry for the little bit of a bloopers and that it's a little slow. I'm busy with some other stuff at the moment, so I'm trying to do my best to get these done for you. I know they are helpful, but yeah, so sorry there's a little longer and maybe less clean than they usually are. Hopefully it still helps. Good luck.